Okay, so hi everyone. Uh, Today I want to talk a bit about the properties of the terrestrial planets. These are the four inner planets, Mercury, Venus, Earth, and Mars, and often the moon, Earth's moon, is given honorary planet status here because it's not that much smaller than Mercury and is also a big rock-rich round object. Now, one thing you will notice about these bodies is they actually are quite diverse. And one of the things about this diversity that is, of course, relevant for our own benefit is just how hospitable they are to life. I mean, Earth in particular, we know, has abundant life. And there's a variety of reasons for that. We have an atmosphere that allows at least us surface creatures to breathe. There is abundant liquid water, which is needed for a lot of life's chemistry. And the surface of the Earth, while variable in temperature, is close to the freezing point and freezing point of water, which means, life can live on the surface fairly happily, at least life as we know it. That's not true for the other planets. Venus, in particular, has a surface that's extremely hot due to an extremely dense atmosphere, which makes its surface nightmarish for life. It's hot enough to melt lead. Mercury and the moon, on the other hand, have no atmosphere to speak of and basically no liquid water. So they're also quite hostile places to be around because you're exposed to basically empty space. Mars is the closest to Earth in terms of habitability. It's got maybe water on its surface. It's got a thin atmosphere, but its surface is actually quite cold. If there's any water on the surface, it's very transient. There might be some just below the surface. So it's the best option outside of Earth for finding life, but even that's not clear. Now, one of the things we want to talk about, though, is why are these bodies so different in terms of not just their habitability, but more fundamental aspects. And the specific aspect that's probably most helpful for getting a sense of what makes these bodies so different is the concept of geologic activity. Now, geologic activity can be a bit of a woolly concept, but what it fundamentally means is something from the inside of the planet affecting its surface. There's two basic types of geologic activity, which are called volcanism and tectonics. Volcanism literally means volcanoes. It's a place where material from inside a planet gets ejected onto its surface. So a volcano, which involves lava or ash being spewed out and covering the surface. That's a fairly clear example of geologic activity. Tectonics is a bit more subtle, sort of. It's a case where something inside the planet deforms or distorts the surface of a planet. That can be forming mountains like the Rockies. That can be forming rifts, basically the surface being pulled apart or crunched together by internal processes. Now, the most dramatic way this manifests for us today is via earthquakes. This moving around of the Earth's surface causes things like earthquakes. And both of these things happen quite a bit on Earth, but they also occur on all of the other terrestrial planets. Volcanoes are seen on all of the other terrestrial planets. This one down here is Olympus Mons, which is a mountain on Mars, and it's an extremely large mountain. It's actually the largest volcano known anywhere in the solar system. And what you're seeing here is material that flowed out through the interior from this caldera all over the surface. Venus has lots of volcanoes. This one is Sapa Mons, which is just a very pretty one. And what you're seeing around it are lava flows. So again, these are classical volcanoes. Maybe extreme examples of them, but they do exist. Now, on the Moon and Mercury, there's also evidence of volcanism, but it's a little different. The discrete structures like the volcanoes we see on Earth, Venus, and Mars aren't there. But they are lava flows, and they can be quite large. This is a picture showing one of those lava flows running through the center. In fact, if you look at the moon anytime it's full, you can see the lava flows on the moon. The surface of the moon has bright patches and dark patches. Those dark patches are actually gigantic lava flows that cover a fair fraction of the lunar surface. The same sort of broad sheet-like lava flows are seen on Mercury. They're not as easy to show in images because they don't have this clear brightness difference, but they are there and you can map them out if you have good data. So we can see examples of volcanism on all of the terrestrial planets. We also can see evidence of tectonics on all the other planets. Again, Mars is a great example. This is Valles Marineris, an extremely large fissure on Mars, or valley, which is a place where the crust has been torn apart. There are similar features seen all over Venus, where the surface has been pulled apart by tectonic forces. These are places where the crust has been pulled apart. On Mercury, we see places where the crust has been pushed together, like along this ridge, which is one of many found on Mercury's surface. And similar things, although not as extreme, are seen on. So we see evidence of geologic activity on all of these different planets. What we're going to focus on, though, is how much geologic activity there is and how important these processes are compared to processes that don't require something to happen inside the body. Now, on Earth, these processes are typically called erosion. Erosion is something that doesn't require anything to happen inside Earth to change the Earth's surface. It's something from outside Earth's surface that affects the surface. So the classic example is, water in a river causes the banks to erode. It causes material to slough down and get transported to the sea. Other processes can involve wind eroding structures in the desert. These don't require any material from the inside of the planet to go outside. There's something that just happens due to its interaction with the atmosphere and its environment. This is common on Earth. A lot of geology on Earth is due to erosion, riverbanks, the creek, things like that. On other planets, though, this does happen, but it's not as important as one particular type of external process, which is impact cratering. Impact cratering is a specific type of process where something outside the planet entirely, an asteroid, a meteor, something that comes from interplanetary space, crashes into the body and produces a crater. It basically blows a hole in it. Now, this is seen rarely on Earth. There's a very nice example down in Arizona called Meteor Crater. But it is extremely common elsewhere in the solar system. There are craters on Mars. There are craters like this one, which is on Venus. There are many craters on the moon and many craters on Mercury. So craters do occur all over the place. And one of the things that's particularly relevant for understanding how active a body is, how important its volcanism and tectonics are, is how much of the surface features are due to volcanism or tectonics versus how many of those features are due to impacts. The reason this is important is because of something called the superposition principle, which is a fundamental rule of geology, which is used to figure out the sequence of geologic events. And what it just says is that later events cover up or disrupt earlier structures. So for example, there's a nice picture here of Mercury. And a lot of what you see here are impact craters. This is an impact crater. This is another impact crater. What you'll notice here is there's an impact crater filled with lava. If you look closely, you'll see there's a little patch of lava flowing through this image. It's filling this crater here and this crater here. Since the lava flowed into that crater, the lava is more recent than that crater. So this lava flowed after some of these craters formed. However, there are also craters like this one, and this one, which are on top of the lava. They happened into it. So there are also craters that happened more recently. This tells us that this lava flowed after some craters formed, but before other craters formed. Now, since the craters are coming from outside, this already is telling us something about the age of this lava flow. And this is the basis for understanding a lot of the history of solar system surfaces. Basically, the more heavily cratered a surface is, the older it is. Because if you make a surface recently, it's only had so much time to acquire craters. The longer it's been exposed, the more craters it could have. And for the moon and Mercury in particular, their surfaces are heavily cratered, implying that they are very old. So they haven't had much recent geologic activity. Now, those are all vague terms. Can we be more precise about that? How old are these surfaces? Well, that's actually hard to answer directly for Mercury, but for the moon, we have hope. Now, important thing to understand is the moon's surface does have a range of different features. There are these bright regions, which are called highlands, and these dark regions called maria, which we already said are gigantic lava flows. We can look at the surfaces and they have very different amounts of craters. This is a piece of the maria. It has quite a few craters. This is a picture of the highlands, which has even more craters, like they're basically filling up the surface. So this has clearly been exposed longer than this has, but how much longer is it? You might naively say, well, there's lots more craters here than here, so this must be much, much older than this. And that would be reasonable. But it's not proof. The nice thing about the moon is spacecraft and astronauts have gone to the moon and collected rocks. They've collected rocks from both the maria and the highlands. Take those rocks to a lab and measure their chemical composition very carefully, you can figure out how old they are. We'll get into how that works a bit later on. But turns out that the rocks from all of these regions are extremely old compared to Earth rocks. This plot here shows the fraction of rocks from the Earth and from the moon that have different ages. And note this is measured in billions of years. The rocks on Earth run from being 0 years old because they just came out of a volcano, some of that's happening right now, over to roughly 3 billion years old. And they're scattered all across. This is because geologic activity is occurring at different rates in different places. Here in Idaho, there are maybe some volcanoes that could erupt, like, you know, if Yellowstone ever does its thing. But there are also reasons that are quite old. But the typical thing is the surface has a range of ages up to about 3 billion years old. The rocks from the moon are all over 3 billion years old. And interestingly, these Maria are 3.5 billion years old, so they're already old. And the Highlands are 4 billion years old. So that's important because it means this amount of craters is what you get being exposed to space for 3.5 billion years. And there's a fair number of craters there. But if you're around for 4 billion years, you have many, many more craters. That means that between 4 billion years and 3.5 billion years ago, most of these craters formed. Most of the objects hit the moon. This implies that in around between 4 billion and 3.5 billion years ago, there was a lot more stuff crashing into the moon than there was since then. Implies the early solar system was a rather violent place. It implies any place that is heavily cratered, like these parts of the moon and most parts of Mercury, are extremely ancient. Now, you could say, well, maybe all the stuff that hit the moon 4 billion years ago, that missed Mercury. That seems unlikely because most of the stuff hitting the moon is thought to come from asteroids and other things that would basically hit all of these objects. It's not been proven, so there's a little bit of argument, but not much. Now, furthermore, in addition to these impacts being more frequent, they're also bigger early on. There are gigantic impact basins on both the moon. This is Mare Orientale, which is on the side of the moon we can just barely see, but it's very clearly an impact crater. And on Mercury, this is a gigantic impact crater called Caloris Basin. These involve objects that aren't too much smaller than the things they're hitting. I mean, they're small enough they make craters and don't break them, but we've never seen an object this big crash into any planet that we've been looking at. There's not even objects around that are likely to hit these objects anymore. So there's good evidence to think that there were a lot more and a lot bigger objects running around the solar system 4 billion years ago than there are today. What that tells us is these heavily cratered surfaces are ancient. It means that even the lava flows on the Mercury and the moon are still old. So Moon and Mercury are basically extremely heavily cratered and imply that not much is happening to their surface today. They're what are sometimes called geologically dead. There is just not much ongoing geologic activity. By contrast, Earth has geologic activity going on right now. It is active. Venus also is probably geologically active. It's hard to know for sure because it's hard to observe its surface cleanly through its atmosphere, but its surface is very much dominated by volcanoes and tectonic features. So if it's not geologically active now, it's been geologically active for quite some time, for quite recently. Mars is in between, actually. There are parts of Mars that are pretty heavily cratered, but there are other parts that have a lot of tectonic and volcanic features. What's interesting about these observations is it shows a trend. The big objects, Earth and Venus, have the most evidence for ongoing geologic activity. The smallest objects, Moon and Mercury, are the ones that are most heavily cratered and have the least geologic activity. That correlation is telling us something. It's telling us something about how these planets work. And specifically, it shows that there's a correlation between geologic activity and size. And we have a good idea of why that is. It's basically, the idea is these planets acquired, it has to do with how these planets' interiors got the way they are. Now, as we already talked about, Earth and probably all the giant planets are bodies with hot interiors. We know, for example, Earth has a molten metal core. And it's quite likely that Venus and Mercury, and you do as well, there's now new evidence that Mars does. Moon, it's a little more ambiguous. Where did that heat come from? Why are the internal parts of these planets so hot? Well, heat is a form of energy. There needed to be energy implanted into these planets deep in their interiors. And that heat is what is driving geologic activity. It is what is throwing material out in the form of volcanoes. It is what is causing things to move around in the form of tectonism. So what this implies is that there is more heat retained in Earth and Venus than there is in Mercury and the Moon. Why is that? Why are Earth and Venus still able to drive volcanism and tectonics, whereas Mercury and the Moon really don't? Well, to understand that, you have to think of where could this heat have come from? And there are three fundamental sources of heat that we can think of as a way to deliver heat to planets. One of those processes is via impacts. If you take an object and crash it into the planet, it's moving fast as it hits in. That's kinetic energy. That energy has to transform into another form when it's stopped crashing into the planet. That goes into the form of heat. Another form of energy comes from what's called differentiation. Remember, Earth's core, and probably most terrestrial planets' cores, are preferentially iron, are preferentially metal, because metal is denser and sinks. The thing is, something sinking is a change in energy. So if you let something heavy fall through air, or let like a rock fall through water, that's releasing gravitational energy. So what that means is if you have metal coalescing towards the center of a planet, that is releasing energy in the form of heat, which makes the rock and other things in the planet easier, more liquid-like, and allows the metal to move towards the center more easily, which can create a runaway process. If it's warm enough to allow some of the metal to move towards the center, that metal moving towards the center and the rock moving up will release heat, warming up the interior of the planet, making things easier to move, and that can run away. Finally, There are certain atoms in rocks, like potassium, like uranium, that spontaneously transform into other forms, producing radioactivity. This is, again, a release of energy. So all of these processes can impart energy into the planet. And the thing is, they're all tied to how the planet formed. These radioactivity came from the rocks the planet was put together from. The accretion or impacts is probably how the planet was assembled. This differentiation process is what happens as those rocks try to settle out. And importantly, all of these processes basically depend on the mass of the planet. The mass determines how fast things hit it. The mass determines how much of the gravitational pull is separating out the metal from the rock. And the mass determines just how many atoms there are that are radioactive. So the amount of energy you put into a planet when it forms depends on its volume or its mass. By contrast, how fast a planet loses energy depends on its surface area. There are various ways that a planet can lose heat. One is by radiation. It just emits light, which of course depends on area. Another way that heat can be lost from the inside of the planet is through convection and conduction. Convection is the literal motion of material. Hot material rises, maybe erupts, cools off, and then sinks back down. That is a way to transfer heat. You take hot stuff, move it up to the cold stuff, and then it cools off and comes back down. Conduction is just the transfer of heat through a solid material, which happens in rocks. If you've ever stepped on a cold rock or a hot rock, you know that, etc. But how efficiently all of these transport processes work depends on how much surface area the heat has to pass through. Now, this is important because if you make a planet bigger, you increase both its surface area and its mass, but you increase the mass faster than the surface area. So as we go from the moon to Venus and Earth, the moon is fairly small. So it has a small volume compared to its surface area. It had less heat and it lost that heat more quickly. So did Mercury. By contrast, Earth and Venus have more volume, they have more mass, so they had more heat to start with. And because their surface area to volume ratios are smaller, they lose the heat less efficiently. So they still are losing heat today in the form of geologic activity. So that basic understanding explains why the moon and Mercury are relatively geologically dead, because they basically lost all their internal heat from formation, whereas Earth and Venus are probably geologically active today because they're large and they were able to hold on to more of their internal heat. This is a useful thing for understanding the basic aspects of these bodies. Now, so that explains both why these are both heavily cratered surfaces. There's another commonality that's related to that, which is neither of these objects has an atmosphere. That is also tied to their size, because by being small, they have a weaker gravity, which makes it harder to hold on to the molecules in the atmosphere. We'll talk about this more in the context of Mars and Venus. This lack of atmosphere actually means the surfaces of these bodies have really weird environments. You know, you might think at first that these would have radically different surface temperatures, and in many ways they do. The moon is orbiting around about Earth, so you might think it'd be about Earth temperature. Mercury is orbiting really close to the sun, so you'd expect its surface to be hot. And in fact, that is true in places. In other places, both of these objects are have extremely cold surfaces. The neatest demonstration of that is from observations near the poles of both the moon and Mercury, which show bright radar returns, here shown as white, here shown as yellow, that are due to large deposits of water ice. Now, water ice on the moon, you might go, oh, that makes sense. There's ice on Earth. Water ice on Mercury is weird because this is someplace that's supposed to be really hot. It's really close to the sun. The reason for the existence of this on both of these planets is because they have no atmosphere. The thing is, since there's no atmosphere to transport heat, the temperature of the surface is basically set by whether you're in sunlight or not. And near the poles here, there are places where there are, especially inside these craters are deep enough that the sun never rises, so they're in permanent darkness. So these regions are exceptionally cold. This is actually a plot of temperature as a function of different colors going all the way down, temperatures shown in different colors ranging from kind of earthish temperatures to extremely cold temperatures right around the pole. In the typical parts of the sunlit moon, it gets up to 260 degrees Fahrenheit, 350 Kelvin. In the places that are permanently shadowed, it's 100 Kelvin or minus 280 Fahrenheit. There are huge temperature swings depending on whether you're in the sun or not on both the moon and Mercury. So there's a lot in common between the moon and Mercury, but I don't want to overstate that. These two objects are also quite different in important ways. The one we've already talked about is they have extremely different densities. The density of the moon is rather low. It's 3.3 grams per cubic centimeter, while the density of Mercury is 5.4, comparable to Earth. This implies that these two objects have very different compositions. Mercury is almost entirely rock. The moon is almost entirely rock. Mercury has a substantial metal fraction. In fact, it's almost 60% metal to 30% rock. Now, that implies that the moon has a small core, whereas Mercury has a large core. And we actually have independent evidence for this. Now, remember, how do we know the properties of the core on Earth? It's through seismology and through the magnetic field. We have done seismology on the moon. The astronauts who went to the moon carried seismometers and measured moonquakes. They didn't measure very many of them, but data from those did indicate that the core of the moon is quite small. Mercury, we've never put a seismometer on. It would be cool, but it would be an interesting measurement, but putting something on an object that gets really, really hot is hard. But what's interesting about Mercury is it has, for its size, a remarkably strong magnetic field. After Earth, Mercury has the next strongest magnetic field in the inner solar system, stronger than Venus, stronger than Mars. That magnetic field is driven by the motions of liquid metal in its core. The existence of this of this strong magnetic field implies that Mercury has a large core, or is at least consistent with that. Now, you might say, wait, if it has a molten core, doesn't it still have internal heat, and then shouldn't it be geologically active? The question is still how much heat that is. The internal parts of both of these planets are still hot, but that heat can be lost through the surface just through conduction. There isn't any need to actually break apart the surface or for volcanism to erupt. They're cool enough that that heat is being now transferred in a less dramatic way. So there does seem to be a big difference in the internal structures of these two guys and in terms of their fundamental composition. Why? Why does the moon have such a tiny core? It's mostly rock, whereas Mercury has an enormous core and is largely metal. This is still something that people discuss. And there are a variety of possibilities, but the one that is currently accepted and is widely understood as probably what happened involves impact events. Now, we already talked about how there are evidence of big impacts in the distant past. Well, if we extrapolate, we could imagine that in the very early part of the solar system, there were very big impacts. Impacts that were big enough not just to make craters, but to fundamentally change the structure of these bodies. And the problem with this idea is it can do almost anything. But the advantage of the idea is that it can explain certain aspects of things like the moon and Mercury. Specifically, if we took something comparable in size to Mercury and crashed it into Mercury, that collision, if done under the right conditions, could have stripped off its outer rocky layers, leaving behind a metal-rich planet that is basically the core of the original planet, with a bit of rock left over. The moon is a bit of a different story. In that case, instead of imagining having a giant object crash into the moon, you imagine an object maybe the size of Mars crashing into the Earth. What happens then? Well, if you do that right, that collision can knock off the outer layers of the Earth, throwing rock-rich material into orbit around the Earth to form the moon. Now, these are nice stories, they're nice ideas. For the moon in particular, we have a lot of information about the composition and structure of the moon that we can actually test this idea. Can you throw enough material out with the right properties to form the moon? And currently, looks like it's doable. Is it what happened? That's still an area of active discussion. So, but it's definitely one of the leading ideas. So, that's most of what I plan to talk about here in terms of Mercury and the moon. In the next presentation, I'll talk a little bit more about the bigger planets, Mars, and then Venus. Thank you for your time and attention. I'll see you next time.